scripts.
Thank you for the organizers for letting me speak here, and thank you for being here. My name is Shang-Shi Kong. I'm a graduate student from Rutgers. I work with Professor Bloomberg. I changed the title of the talk a little bit. So today I'm going to focus on the symmetry breaking in the hidden order phase of URS. Another URS talk. All of the data can be found in our paper, science paper published last year in Science. First, I would like to begin by thanking collaborators. Ryan and Eric, they grew the single crystals. And Werner and Wei Lu, they helped me with the experiment. Christian Hawley from Rutgers, he did a DFT plus DMFT calculation and many theoretical works. John Maidash and Bloomberg, they designed the experiment. I would also like to acknowledge our funding agency, NSF, USDOE, Los Alamos, and ICOM. So as Brian and Rebecca already told us a lot about this material, it's truly enigmatic to be listed in condensed matter. So this is a phase diagram you have seen many times. As Rebecca has told us, this phase transition at 17.5 Kelvin is very mean field-like, so there must be an order parameter or symmetry breaking associated with it. And the biggest question everybody is asking is, what is the order parameter of the hidden order? And as an experimentalist, I'm going to step back a little bit and ask myself another similar question. What is the symmetry breaking at this second order phase transition? And hopefully that would give theorists some kind of hint or starting point to work out the order parameter. So in this phase diagram, you have seen this by pressure or by iron doping, by many other tuning parameters, you can very easily go into an antiferromagnetic phase. Or if you cool down, you can go into a superconducting phase. So in this talk, I'm just going to focus on the hidden order phase, so just the symmetry breaking inside the hidden order phase. And this is the crystal structure of our material. It belongs to the D4H point group, so this will be our starting point. Now, one of the issue about this material on the theoretical side is that, like Brian told us, this is the 5 electrons, uranium 5 electrons have this partly localized and partly itinerant character. We know that 8 electrons in general quite localized, but for uranium 5 electrons, as you see here, here are many uranium compounds. Some of them has a very itinerant character, some of them has very localized character. And URS, we're going to hear more talk about it, and those people has already demonstrated is at least partly localized, partly itinerant. So theoretically, it's difficult to deal with. And on the material side, because we see in the phase diagram, there's this very close by antiferromagnetic phase. Therefore, as Mizuka Edo has shown, and I think many other papers have shown, that this supposedly very sharp first order phase transition can be broadened if there are strain in the crystal or defects or something. And that is because once you have strain field, so strain field can push little particles in the crystal into antiferromagnetic phase, so you get all these magnetic particles in your crystal. And when you are measuring, you get the signal from hidden order and from antiferromagnetic phase. And this is just, for experimentalists, it's difficult to figure out which one's which. And that is a lot of confusion for many years. Recently, like by Stanford group, by Young Fisher, and by Japanese group, by Matsuda, and by many groups, they find that there's some of the features has to get only see in those very fine small crystals, where they believe the triple R is extremely high and is really strain-free. For us, we do Raman scattering, that is an optical probe. So what we do is that we focus our laser spot onto a small portion of the crystal where we believe it's strain-free and is as nice as we can get. So this is a crystal under the so-called Nomarsky or phase contrast microscope. So Nomarsky microscopy is widely used in industry, actually by international airlines. You know, that's how they look at the airplane to see if there's any strain field in the wing. So the material don't want anything bad happen to that. Right? So basically in Nomarsky, the strain field reflects as color contrast. So here, for example, here, like a very uniform color, that means it is strain-free. And places like this and this, they have the color contrast as a strain field. And this crystal is, in general, already very, very good. In some of the crystals, it's like a rainbow. So some of the crystals, you can really see the strain field very, very clearly. And this is roughly our laser spot size, so we will pick this area to do our experiment where it is really strain-free and nice. And as I mentioned before, this talk is going to be focused on the symmetry aspect. So in the D4H point group, those are the irreducible representations of this group. And those are the ones that did not include the gamma 6 and gamma 7, that's Crummers doublet. So those are the A1G to EG, or some people prefer gamma 1 and gamma 5. Those are the ones that preserve invergent symmetry, and those are the ones that are the invergent symmetry. Now please pay a particular attention to this A2G gamma 2. This symmetry channel is unique in the sense that it breaks both the vertical and the diagonal refractions. So it transforms like RZ as a JZ, transforms like a pseudo vector along Z direction. And this is in fact a very interesting channel for us, for Raman scattering, because we find that this channel usually is zero for most of Raman scattering experiments. But in this compound, we find a lot of signal in this. In fact, it is the only channel that has temperature dependence. But we'll get to that later. So Raman scattering, as you know, it is basically inelastic light scattering. So you excite with an incoming light, you excite the electron to some intermediate state, and come back into the scattered light, come back to the excited state. You measure the energy difference, and that's called the Raman shift. Now, by using the polarized light, we can pick out the specific symmetrized excitations. For example, in this what we call XY geometry, the incoming light we come in with X. What does it mean? It means that the polarization of the incoming light is along X direction, which is aligned with let's say 100 crystallographic axis of the compound. And the scattered light, we pick light that's polarized along Y direction, that's 0, 1, 0 of the sample. And the Raman tensor dictates that in this symmetry in this geometry, we will couple to B2G and the A2G symmetrized excitations. And indeed, back in the 80s, Lance Cooper et al. Already find that in this XY geometry, you have this quasi-elastic peak developing as you cool down the sample. And in our experiment, we did more geometries and we further isolated just the A2G part. And we find that it's really this quasi-elastic peak is due to the A2G part, and you can see that this peak maximum slowly softens towards 0 as we cool down the sample. That is looks like a damped excitation where the lifetime gets longer and longer when you cool down. But what's also this experiment was also done by another group in France, and they have the same conclusion. First of all, to see a continuum in A2G, in a non-magnetic metal is already very, very rare to be like this. And moreover, what happens is that in the hidden order phase, we see an opening of a gap in the continuum and the appearance of this very sharp and quite intense collective mode. Now, this energy gap is about 6 MeV. That's roughly the energy gap seen by IR spectroscopy. Moreover, this collective mode happens to be at the same energy, about 1.6 MeV. That's the same as this dispersive mode seen by inelastic neutron scattering at the zone boundary 100. So the identity of this collective mode is really interesting, but however, I will not go into the detail here. So Professor Bloomberg is going to talk much more about the origin and the property of this mode. To really study this collective mode, you have to have something to tune, and you have to study the entire phase diagram. And thanks to Brian's crystals, we were able to do that experimentally. Here, this is the carbon plot of the low temperature Raman scattering response in the XY channel, in the XY geometry. Yeah, you can really see that this gap opens up below the hidden order transition temperature, and this mode also appears at this temperature. Now, in this talk, I was come back and focus on the symmetry. And so in order to figure out the symmetry breaking inside the hidden order, what we have to do is we take all 6 so-called proper scattering geometries. That's the scattering geometries that contains all of the symmetry channels available to Raman scattering in the AB plane of this D4H crystal group. So you see that first this sharp collective mode happens appear in all geometries containing A2G symmetry at those 3. But if we look at it more closely, we find that there's a non-zero intensity at the exactly same energy, and they have repeated, they have roughly the same lifetime as this collective mode. And we know that this is not due to polarizer leakage. We measure the phonon, so it cannot be due to this misalignment of crystal, because we measure the phonon. There's no leakage there. And usually this kind of sort of leakage indicates that there must be associated symmetry breaking. Now the question is, what is the symmetry that's broken in order to allow this kind of leakage? Now, this is the character table of D4H group, and we find that in order to have the leakage, we have to remove those sigma B and sigma D, that's the reflection symmetries. If we remove those, we go into a lower group, that's C4H group, where we find that the A1G, A2G, those 2 irreducible representations now merge into AG. B1 and B2, they merge into BG, and the EG remains the same. And this sounds all very complicated, B1, B2 stuff. But so what it means is that, for example, if we have a purely A2G collective mode, in D4H group, we would expect to appear in those places where it has a little tip here. That's XY, X prime, Y prime, the RR scattering geometries. We should expect them only appear in those 3. But if it's in a C4H group, we would expect them to appear in those 5, but not in the RL. And this is indeed what we see experimentally. So we see this mode appears in those 3 geometries, XY, X prime, Y prime, RR. And we see a small intensity in those 2 geometries containing A1G. That's A1G of the D4H group. Now we are in C4H, it's actually, they are all AG. Now, but within the noise, we don't see the RL. So this is all very consistent, and that really means that we have a reflection symmetry breaking in the hidden order phase that we can see directly by experiment. But you would ask, what does that really mean? What is the consequence of this reflection symmetry breaking? Now, one example that I show here is if we use this crystal field states to demonstrate. It's not limited to this, but let's say this is I think it's a nice example. So, for example, if we have let's say 5A2 electrons from the bicarb subshell, and if they are in the D4H crystal field, they will split into 7 states. Now, according to Howler and Cotlier's EMFD plus DFD calculation, the lowest 2 states are A1G and A2G symmetrized. Now, many people will not disagree with this, but let's say, for the sake of argument, let's say this is the lowest state. Now, if we plot the symmetry of this, the amplitude of those states, they look like this. So in A1G, it has all of the symmetries of the D4H group. In A2G, it breaks all the reflection symmetries. Now, if the reflection symmetry is intrinsically broken in this hidden order, then what happens is that it allows A1G and A2G states to be mixed by proper operator. And the mixing of it will allow this A2G state to look like this. So depending on how you mix it, you can have a plus and minus sign, and then you actually get this kind of states. And you can see that those 2 states cannot be reflected onto each other by simple reflection. So there's always a minus sign. And you cannot rotate them onto each other either. And this is really like our left and right hands. So what it means is that when you break the reflection symmetry in a D4H group, what you get is the emergence of what they call handedness or chirality. So this is a surface example of what's the consequence of this reflection symmetry breaking in the hidden order phase. This is a new type of ordering that we can get. So in conclusion, we see in-gap collective mode that's in the A2G symmetry in the hidden order phase. And more importantly is that we see a reflection symmetry breaking in the hidden order phase. That's by experiment without any assumptions. And the emergence of a chirality that comes from this reflection symmetry breaking, if we further stagger it, so it doesn't really matter where those which model you adopt. This the emergence of chirality comes quite directly from a symmetry point of view, and whatever state you like to stagger, it gives you basically have a chirality density weight, and more details can be found in our paper, and that will be all of my talk. Yeah, thank you.
So we're open to questions. There's one right there.
Okay, so this follows on my previous question, but I want to separate it from static order and connected order data. An A2G symmetry excitation can be an excitation from gamma 1 and gamma 2. So it can be an excitation of half pseudospin, or it can be an excitation of a gamma 5 pseudospin where you're flipping around the z-axis. It looks like a sigma z operator on the gamma 5 pseudospin.
Sorry, from gamma 5 to where?
From gamma 5 up plus gamma 5 down, so gamma 5.
But those are degenerate states, so it won't give you finite energy, right?
Right, no, you have to, what I'm saying is it looks like not excitation, it looks like a flipping of the gamma 5 pseudospin or a flipping of the gamma 1 and gamma 2 pseudospin. So if you have coherence within gamma 5, which is a local order parameter that includes orientation, then you're not, that's very similar to having coherence within gamma 1 and gamma 2.
That's a zero energy excitation.
It's zero energy in a crystal field picture, but not it's a many-body picture. That's the distinction of the many-body order parameter is something that gives you a local orientation for structure, either of these, well,
That requires the gamma fiber state.
local, yeah, not in a
Globally,
global picture.
in any picture.
Yeah. No, I'm speculating separately that this would require the gamma 5 to split with various order parameters for gamma 1, gamma 2, also include a coherent sort of orientation of these sort of humming thing potentially in the same sort of spin.
But Andrew, but wouldn't I expect that if this is within gamma 5, then I should, because gamma 5 give me like gamma 1, 2, 3, 4, right? Shouldn't I expect to see features across other symmetry channels in your picture?
I'm not sure. That's a question for you actually. But I'm asking how can one discriminate between the two pictures? I don't actually have.
Yeah, I think
case, so this is very.
So I think there is experimental answer to that, and namely application of the field will separate this. If the magnetic field along C-axis is applied, they will behave differently. In fact, the dependency on field, I don't know whether you have that slide, behaves as singlet to singlet transition. And if it starts from gamma 5, dependency will be
Gamma 5, yeah, it will.
as a function of field.
That sounds very reasonable. And my question is very, very open-ended, so let's leave it at that.
Let's move on to the next
That
question.
transparency is the answer to it.
I have a question for the data. There has been this other group, this French group, I think it's the first author. I don't think there has been recording this leakage in these key channels.
Yeah.
Is this being sorted out? This.
Yeah. I don't think that they have. Okay. So they still haven't seen the leakage, as far as I understand. And my understanding is that because experimentally, they use a green excitation, so they use a different excitation, and there's some resonance effect, but let's not even forget about that. So I have tried green, and the reason I don't use green is because the luminescent background is huge in green, and they argue that it gives them more signal and it's more closer to resonance and stuff. But experimentally, I think this background is just going to make my signal to noise ratio worse, and that's my understanding of this inconsistency. But they have not tried the infrared in their setup. They have not tried the infrared excitation I used in our experiment. So there's still some. Answer?
How sensitive are you to misalignments?
Misalignment? That can. Yeah, so we use a phonon as our major alignment. Here, basically, that's a picture. So, of course, this is now in 7 Kelvin, but of course, I align at higher temperature, at room temperature. So, where the signal is actually larger. So I align it such that where I shouldn't see the phonon, I don't see the phonon. And as you can see, this can be extremely sensitive. Yeah.
We have time for one more question.
So there's many ways that I can reduce D4H, right?
Yes.
Are there other possibilities that would lead to these things showing up in where they shouldn't, XX, X prime, X prime? You pick one, right? But there is.
Yeah. Not in the scattering geometries available to Raman scattering.
No, I'm asking about the group theory. Maybe if I break inversion symmetry, right? These guys. Is that enough? No. What other possibilities are there?
No. So to our data, no. Yeah. Within our data, there's no other possibility. There are no other possibilities.
Okay, thank you for today. Chairman